G'day, my name's Peter Selby, and this is the second video in a two-part video, which is really a deep dive into how Peltiers work. Now, it was all triggered by my Peltier-based air conditioning system here, which was working great last night. It was producing about 250 watts of heat with just 85 watts into the system. That includes the fans as well as aquarium pumps. So that's a system level COP of around 3. And surprisingly, 250 watts was enough to keep the room at around 21 degrees stable, even though it was 4 or 5 degrees outside and one of these really windy days here. We're about an hour and a half south of Nagoya. We don't get quite as cold as Nagoya does get, but we get incredible winds here, which just really stress your heating systems. But despite that, just 250 watts was enough to keep the room stable. Now, the reasons for that is partly it's a modern house, so some really good wall insulation here. You might have seen in a previous video I've been putting cardboard on the windows there. Windows are terrible for leaking heat, but now I've got these double layer honeycomb blinds, which are doing a great job. Plus, there are other sources of heat in the room, like my body heat, the laptop, the monitor, lights, and stuff like that. So altogether, that's enough to keep a modern house, stable temperature with just 250 watts. Another point of reference, my dirty big air conditioner up there, it's a 6 kilowatt system, I think. In this kind of middle of winter kind of thing, it only gets a COP of about 2 when it's running really hard. But when it's actually tailored back to around a few hundred watts just to keep the room stable, its efficiency is only about 1 to 1. It's COP of 1. That's kind of a surprising secret for those kind of air conditioners. So for that, my Peltier-based system, even though it's just an amateur setup here, was already beating the competition by about a factor of 3. All of that is really beside the point. The big thing was that when I was playing around with that air conditioning system, I stumbled across a COP of 30 under a special condition, but still a COP of 30, and that spun me out, and that's really what triggered me to do this deeper dive into how Peltiers work. So in that last video, I introduced just quickly how that, or the components of that air conditioning system. We had a look at a simple model for Peltiers, just a thermal model there. We looked at an interesting experiment to illustrate some of those characteristics, and then the formulas that apply to Peltiers. But despite all of that material being it's scientifically accurate, it matches what the experts say, there are still 3 things that came out of that which I had problems with. Number one is, how can I get decent performance out of my systems when the experts seem to think that Peltiers are kind of a joke? Number 2, this Carnot theory and the ZT theory. Something is wrong there because it seems to not line up with what I'm measuring, or it seems to blow up at that DT of 0. And number 3, all of this really doesn't explain how you get this COP of 30, what's happening there at the deep molecular level. So hopefully this video will tie all this together and give a good explanation. So let's kick on. I think the first one is going to be digging into this performance as well as the ZT Carnot theory stuff. Okay, let's get into it. Okay, it's time to dig into this discrepancy between the decent results I'm getting out of my systems versus the popular view that says Peltiers are little more than a party trick. Now, this splits into 2 problems. One is mathematical mistakes and the other is implementation mistakes. And I've covered this in a video before, but now I have a more refined view after this deep dive. I think it's worth to look at it again. Now, this split between the mathematical world and implementation, actually I have this problem a lot in my work as well. I'm a design engineer, test engineer. I have a lot of ad hoc circuits or experiments, and I worry about making mistakes. So I always try to do a prediction based on the maths or theory, the physics and so on, and then I will do proper measurements, and then I put those 2 together, and if they match, that's kind of a double check to make sure I haven't made any dumb mistakes. But it happens quite a lot where I have dumb mistakes in my prediction side and dumb mistakes in my implementation side, and they just happen to independently come out to be the same result. So I think everything's okay, even though there are these underlying problems in my actual work that I'm doing. And I think this is what's happening with the Peltier on the math side. The mistakes predict poor performance. The implementation side, the mistakes are causing poor performance. Those 2 are coming together and reinforcing each other, and also reinforcing this view that Peltiers just are not very efficient. All right, so I will split that into the 2 parts, the math side and the implementation side. So the first will be those mathematical errors. Okay, for this segment, I'm going to use a checklist here to try and keep me on track. There's a lot of small points to make. They're all quite interesting, but I just want to make sure I get through them all without going off on a big tangent somewhere. So the first item on the list says refrigeration. So my thesis here is that all of this stuff was developed at a time when refrigeration was the main game and you need a DT of around 60 Kelvin. And I agree that Peltiers just really suck at that kind of level. They're probably around 5 to 10% efficient, and that's probably where that figure of 5% originated from. Now, of course, in the modern world, there are applications that have much lower DT. For example, my geothermal system, it's running at DT of between 5 to 15, and I'm getting efficiencies of around 200 to 400% depending on the conditions. So obviously that 5% figure doesn't represent the whole range of applications. The second item on the list here is this ZT figure. You see that popping up quite a lot in literature. Again, I think historically this would have made a lot of sense when you're comparing different types of material and you need a metric to say which one is better, and that ZT really worked quite well. It's a ratio of the good stuff divided by the bad stuff. So yeah, it makes sense there. But mathematically, once you've sort of stuck on a particular type of material here, it's too mathematically complicated to provide any value, and people just make a lot of mistakes with those numbers. So for example, the common figure that people say for ZT 1.0, I think, that's actually wrong. It's a figure that comes from laboratory testing for bulk material under ideal conditions at around 450 degrees, which is totally different to the modern production level room temperature kind of applications, where the ZT is actually 0.3, so it's 3 times worse than what they're saying. But then what does 0.3 mean anyway? You have to plug it into that formula. You have to know what your TC is, your TH, delta T, as well as the current that you're using. There's so many factors to figure out that the ZT just becomes kind of useless compared to the simplicity of just using that QC equation and the power in equation that I gave you in the previous video. But sticking on that, I do want to just talk a little bit more about this ZT and the Carnot theory. So the first issue is this apparent ratio from the Carnot theory, the TC divided by delta T, that pops up in the ZT calculation, the COP max. So I'll put those on the screen for you to see. It looks as if there's some deep fundamental connection there to the thermodynamics and second law of thermodynamics and the entropy and so on. Turns out that this is just a mathematical coincidence. The method to derive that ZT related equation, it takes the COP based on QC and power in. I covered this in the previous video. A bit of maths, calculus and so on, and you can figure out where the maximum is, and it just happens that this Carnot ratio pops up in the formula. Whereas the Carnot theory is developed from entropy, second law of thermodynamics and so on, totally different method. It just happens to get the same ratio there. And even the people that made this formula, they said don't read too much into the fact that Carnot theory stuff appears into that ZT equation. But despite that, both equations do blow up at dt of 0. So what's happening there? So I want to go back to that QC equation. It has that 3 components there, the alpha Ti minus a half I squared R minus K times delta T. So all of that is really just those 3 independent components, the wonderful heat pump effect, the I squared R losses, the joule heating, and then you have this leakage component, which is just normal conduction, thermal conduction through the Peltier from the hot side to the cold side. And you can see from that formula, if you have, say, a dt of 0, the other 2 just keep ticking along quite fine. You still get that wonderful heat pump effect, and you also get the I squared R effect, the negative effects. So even at a dt of 0, you're not going to get an infinite COP, but everything else just keeps ticking along fine. And if you have a positive, a negative dt, so this is defining where the cold side is actually warmer than the hot side, what happens there? Well, it's just leakage happens as you expect, but it happens to be in the same direction as the heat pump effect, so it's kind of assisting the system. Still nothing special to see there. So this whole thing about a dt of 0, there's nothing that happens fundamentally at the Peltier level. So what's happening mathematically with the ZT equation? Well, this one I can confidently explain. So it turns out that if you do have a dt, the equations are a bit messy. So I'll pop it up on the screen. So for the COP, you have a linear relationship with the current, you have a squared relationship, and then you also have a constant on the numerator. And then on the denominator, you have another squared factor and another linear factor. So all of that's going to mix together to create a kind of weird shaped curve. Which you will see in the data sheets. And from that, of course, if there is a maximum in the curve, you can do your calculus to figure out where that maximum is. However, when you have a dt of 0, the special condition, that equation collapses down to something very simple. It's just a constant divided by the current minus 0.5, basically a 1 on x shape. A 1 on x shape doesn't have a maximum. So if you try to do a mathematical analysis to get this maximum, you're just going to fall over and face plant. So that explains why you can't get a maximum COP from a dt of 0 using those equations. What's happening with the Carnot theory? I don't know enough about it to talk about this confidently, but I'm suspecting something similar is going on. The equations that describe the COP as a function of work in and the temperatures and so on. Probably the original curve is fine. It doesn't blow up or anything, but there is no maximum. So if you try to apply calculus to figure out where the maximum is, it's just going to fall over and face plant as well. Okay, so basically that's it. That's the mathematical mess ups that people are making. I do just want to summarize here to say, if you want to play around with Peltiers, the best thing you can do is to use the QC and the power in formula, or use that model that I showed you, which has those 3 components in there. That works great. You can put it into circuit simulators. You can add in things like your thermal resistance on your heat exchangers, your insulation in the system. You can model the whole system very well and get some really good results that match the actual the measurements that I get from real world systems. Okay, so that's it on the mathematical side. Okay, it's time to talk about some of the practical problems people are making when they do Peltier applications, and by far the biggest problem is just not managing your thermal resistance outside of the Peltier itself. So for example, my air conditioning application here, it has, you've got thermal coupling between the Peltier and the aluminium blocks, and when the aluminium to the water circuit to the upper heat exchange, and then from that to the air here. So you can lump all those together as a single element if you want, but you still need to understand what all of those are and minimize them as much as possible. You're going to have similar things on the cold side as well. So to illustrate this effect, I want to go back to my first video where I introduced a model that had 3 simple components. There was the wonderful heat pump effect. You had the leakage from the hot side to the cold side, just the thermal conductivity, and then the I squared R effect. And what I want to do is, first of all, to take away the I squared R effect, just to make it simple, to illustrate the point. I'm going to turn it on its side so it looks a bit like a battery, and then I'm going to run the Peltier effect at around 30 watts. This is like a good zone for me, and we're going to have an internal resistance, round numbers, of 1 Kelvin per watt. So if we had this just a Peltier sitting in air and it's not thermally conducted or coupled to anything, you would get that 30 watts is just going to circulate internally and create a temperature difference of 30 Kelvin. So hopefully that kind of makes sense. It's a fairly simple circuit there. Now, in my case, I like to use thermal resistance. A target for my thermal resistance is around 10% of the Peltier's internal resistance. So in this case, I'd be targeting a thermal resistance of 0.1 Kelvin per watt or less. So let's put that into the circuit there, and hopefully it should be obvious that the 30 watts that's coming out of the heat pump effect is going to see the internal resistance 1 Kelvin per watt, the external resistance 0.1. I'm going to go outside if I can, and it will. So you'll get, say, roughly 27 watts outside and only 3 watts inside. So that's probably, you know, a fairly good optimum condition. Now, for real world applications, people are using heat sinks like this guy here, or heat exchangers like this. So you've got a aluminium heatsink with a fan on it. I pulled this out of a fridge. I measured this at 0.5 Kelvin per watt, which is already too high for me. But in its in situ application, where it's sitting underneath the cover and you've got only some vent holes to let a certain amount of air coming through here, I'd guess this would be more than 1 Kelvin per watt. And on your cold side, you're going to get something similar as well. So overall, you could easily have 2 Kelvin per watt for the thermal resistance. So let's put that into that circuit there. And now we can see that that heat pump effect, a wonderful 30 watts, is going to look at the outside circuit and say, nah, I don't really want to go there. And so most of the heat is going to go inside. So you get 20 watts of heat going internally, just circulating around, just throw it away, completely useless, and only 10 watts out of that original 30 watts is going to go outside. So hopefully that makes it very clear how important it is to keep your thermal resistances down as low as possible. Now, I have ignored 2 effects here, or in fact 3 effects here. So I've ignored the I squared R effect. I've also ignored the fact that real world systems will have a temperature difference that comes just from the natural application. And then also we have this Seebeck effect, which increases the power. So what I've done here is to use a circuit simulator, and I've got the true values for the whole setup here, which is simulating my air conditioner system here. So I've got, so I should point out that all the components here, of course, are electrical components, but they represent the thermal characteristics. So current is heat flow in watts, your temperature is represented by volts, and the resistors all represent your Kelvin per watt. So you can just put all those numbers in, plug it into the circuit simulator, and it will give you the results without having to go through the complicated maths. So this model represents 1 Peltier out of my air conditioner system here. And I'm using 50 millikelvins on each side, or a total of 0.1 Kelvin per watt for the total external resistance. And you can see the numbers there. I'm getting a COP of around 2 for cooling, 3 for heating, and most importantly, I am getting more heat pump effect out of it than I'm actually putting in. So it shows that we can get decent results out of Peltiers despite the temperature difference there of 10 Kelvin. Now let's replace those 50 millikelvin resistors with 1 Kelvin per watt and just run the numbers again, and you can see that the cooling has just crashed here. It's gone down to 25% of what it was before, or a quarter, and the COPs have just crashed as well. And really, it's just not worth, from a heating point of view, it's not worth going through all the effort here, because pretty much the heat that you're getting out of the system is almost the same as what you're putting in. And if we want to just go one step further and say, well, how about we just sort of push these Peltiers a bit harder, so we double the current, it doesn't really change anything. The cooling power does increase, but it's only just incremental. We're getting way more I squared R losses there. I squared, of course, means if you double the current, you're going to get 4 times the heating, and it all just gets worse. The Seebeck effect gets worse. Just the whole situation just gets worse and worse. So really, you need to manage your thermal resistances and keep them down as low as possible. Now, the stuff that I'm doing here, it's all just a local hardware store and stuff I bought from Amazon. So it's not rocket science. You don't need to go to NASA to find materials to do this kind of thing. You just need to be aware of managing those thermal resistances. Okay, so to summarize all of that, the whole section on the disparity between why I can get good results despite the theory and the experience of other people. Number 1, if anybody starts talking about ZT, just tell them, don't worry. If they start talking about second law of thermodynamics, just tell them, don't worry. And if they still claim that they're not getting great stuff out of their practical applications, well, again, ask them, have you managed your thermal resistance? All right. Despite all of that, I still don't have a good explanation for how I got that COP of 30, which was the original trigger for this whole video. So let's start exploring the true magic of a Peltier. The next part of this story goes all the way back to 1987, when I was a fledgling technician working for the Sydney County Council, and I was asked to make a presentation on these guys. They're called thermocouples. I had to do an explanation of the Seebeck effect, which is how you get a small voltage here based on a temperature difference between the end of a thermocouple and the point where you measure that voltage. Now, ever since then, I had a really good understanding of how thermocouples work, and for the next 38, 39 years, I thought that was how Peltiers also worked. It was just a reverse effect. It's an easy mistake to make. Like, this guy is converting heat to electricity, this guy electricity to heat, this guy has to have 2 different types of metals. This guy has to have two different types of metals. So it seems to make sense that they're just the reverse of each other. And it wasn't till maybe 3 to 6 months ago I started pulling this apart and realizing something didn't make sense. Almost like putting a square peg in a round hole. It didn't add up, and I eventually realized no, they're actually two different effects despite what the literature says. So let's do a quick and dirty explanation of how thermocouples work to start off with. So inside a thermocouple you have a metal, and metals of course have this sea of free electrons, like a cloud of electrons that can move around freely. And just like gases and liquids, if you apply a temperature difference, you'll get a density difference. This is just the kinetic energy sort of pushing stuff around. So you get tighter groupings over here where it's cold, I think, and then less dense where there's higher temperatures. Now, because electrons are charged objects, if you have more of them over here versus over here, you'll get a voltage difference. So it's as simple as that. You have a temperature difference creates density difference, density creates a voltage. Now the problem is, if you wanted to measure that or try to make a thermocouple, you have to have two wires there to get the voltage back. And if you use the same material, say copper going out and copper coming in, you'll create this small voltage there, but it will cancel itself out. So you'll get 0 millivolts here at the end. So you need two different types of material, say copper going out, aluminium coming back in. Both of them will create this small positive voltage, but the key point is that that voltage will be a little bit different for the different types of metals, and that will give you something to measure at the end here. So that's basically how thermocouples work. Peltier devices, totally different. If we keep going with the copper and aluminium, imagine just a single electron that passes over from the copper side to the aluminium side. Now it turns out that in the aluminium, the electron needs a little bit more energy to survive in the structure over there. So it has to get that energy from somewhere, so it takes it out of the bulk of the aluminium, and so that's a cooling effect on the aluminium. The reverse thing happens if the electron travels from the aluminium side to the copper side. It ends up having a little bit extra heat there, so it gives that off to the bulk of the copper there. So that's the basic idea behind a Peltier effect. Now, there's a couple of things there. So first of all, this idea of moving energy around between the structure and thermal, it's the same kind of thing that happens in other types of heat pumps. So for a compressor-based system, you're getting a shift of energy around because from a gas to a liquid, the structure takes more or less energy, and so it either gives up the energy as thermal or takes the energy from whatever it's connected to. So that's basically the same thing that's going on there. Another thing is that although we're talking about a single electron here, of course in the real world Peltiers we talk about current flow, and current is really just a measurement of electrons per second. And power is also energy per second, or joules per second. So we can see that there is this tight relationship for a Peltier between the current that flows through here and the power that's being created, that heat pump effect. And not just a tight relationship, it is a very precise and exact relationship between the current that flows through here and that heat pump effect. Okay, so that's basically the how that effect works, but still there's a few more things that need to be pulled apart here and put back together before we can really get a deeper understanding of Peltiers. Now, while trying to get my head around the whole Peltier thing, I started playing around with a fun analogy called the Peltier mountain. So it starts off with an electron. It's driving around in a car, and it sees this attraction on the side of the road. There's a gate there that it has to drive through. It's called the Peltier mountain. As it goes through the gate, it gets hit with a $10 fee. Now, it's a fixed fee. It doesn't matter how fast it drives through that gate, whether it's 100 miles an hour or just walking speed. It's always $10. As it goes through the attraction, the owners want to encourage safe driving, so they also penalise the drivers with a separate penalty for maybe velocity squared to try to map to this I squared R thing. And then when the electron leaves the mountain, it actually gets the $10 back. So the point being there that even though the plus and minus zero, so plus $10 here, minus $10 over here, they occur at different locations to allow that heat pump effect to occur. So it was just an interesting way to explore what's happening there at the fundamental level by looking at a single electron as it goes through the whole system. Now it turns out there's a few problems there. I realized the first thing was what I call a fence post problem. So a typical Peltier, like this has 127 junctions in there. 2 spots are going to be for your leads here, so that gives you 254 spots for the actual semiconductor cubes, and then there's P and N types there, so that gives you the 127 elements. Now what I realized, if you watched an electron that's actually flowing through here, just a single electron, there is a mismatch between the P and N junctions versus the NP junctions. And you can see this a little bit more clearly if we just slow it down to just 3 PN junctions, so PN, PN, and PN, and imagine the electrons going through there. So you'll have 3 PN actual junctions that it flows through, but only 3 NP. So it could be 3 cooling events and only 2 heating events. So this didn't make sense to me. Eventually, I realized there's more to the structure inside here. There are other conductors in there, and typically it could be copper. And what you have is your copper for your incoming, and that will blend to a P element, and then the P to copper, copper to N, N to copper, copper to P, and so on through the Peltier there. So there's a lot of P to semiconductor junctions through there rather than actual straight P to N junctions. And what happens is that these copper to semiconductors halve the effective Peltier effect. So let's say, to use that $10 I mentioned before, so copper to P would be $5, P to copper would be minus $5, copper to N would be minus $5 again, and then the N to copper would be plus $5. So you get an exact match on each side, so plus $10 over here, minus $10 over here, so it all adds up in the end. So that explains the fence post problem. It's just a little bit more inside there than you might expect. The other problem was whether or not I should be using V squared as the penalty. So there's a transport cost to push the electron through the material. So the P and N materials themselves are resistive, so some energy will be required to push them through that. And it turns out that's just proportional to the velocity. It's not velocity squared. I could go on to explain why, but eventually it makes sense that it's just a velocity. And so the key point for this is, if you're going to look at the COP, the coefficient of performance of just a single electron, what you find is that you have a fixed energy cost. So there'd be some nanojoules per electron or something for every electron that crosses over the barrier. And there is another cost, or divided by the energy cost to push it through, which will be proportional to the velocity. So you end up with a constant divided by a constant times the velocity, so essentially constant divided by velocity. And this matches to that higher level equation that we mentioned before, the QC divided by power in. When you have a dt of 0, this collapses down to just a constant divided by the current. And that makes sense because current is really just the velocity of the conductive elements. Kind of explains why we can get such high COPs if we keep slowing down the current. So instead of using 3 or 4 amps, we use 300 milliamps or even 100 milliamps. We're going to get these fantastic COPs because of that basic relationship there. Okay, so that's my Peltier mountain learning experience. There's one more area that I want to discuss here, and that's going to go back to the Carnot theory. Now, earlier on, I told you not to worry about the Carnot theory. It's just makes things too complicated and not really useful for day-to-day kind of calculations. You can just use that QC and the power in formula, and I definitely recommend that approach for day-to-day stuff. But if you want to understand a bit more about heat pumps and really what's happening at the sort of deeper level here, it's worth going to the Wikipedia page for the Carnot cycle, just to show what they've got wrong there. Well, not really wrong. The theory, of course, is right, but the way that they've presented it is really misleading. So the first thing you'll see here is a diagram that shows the relationship between the hot side, the hot reservoir, the cold reservoir, this QH and QC and work and stuff, and that makes it look as if it's a linear system. That's something's flowing between all those different parts. But actually, a real heat pump is highly dynamic, not only for time, but also the different locations. There's stuff that's happening all over the place. It's literally like a truck that goes over to one place, picks up some heat over here, drives around over to this side here, dumps the heat over here through some mechanism over here, and then has to drive over here again, pick up some more heat again. So there's a whole bunch of stuff that's happening, different locations, different times. It's not just a simple linear relationship like that diagram shows. And it's the same thing with a Peltier. If you look, go back to that diagram where I was trying to figure out that fence post problem, and you start realizing there's different stuff that's happening. If you imagine the electron flowing through the Peltier, you've got the plus $5 that occurs at this point here. Then you have the transport energy. There's just lots of little stuff that's happening at different locations, and that's why you can't really think about it as just sort of heat flowing through here in a kind of linear fashion. So, okay, I think that's the last point that I wanted to make on the theory before I go to the final summary and observations. So we've got to the end of the second video here. I know both of the videos ended up being a lot longer than what I was hoping for, but, well, Peltiers just really are interesting devices, and there's a lot of negative opinions out there and a lot of misinformation, so it was worth to spend a bit of time working through all those issues. Now, as for the main question, what does a COP of 30 mean? I'd like to go back to that original equation, the QC equals alpha Ti minus a half I squared R minus K delta T. And I think that that label on the left-hand side there, that QC itself is a little bit misleading. It really should have been something like Q net equals QC minus a half QJ minus QL, to really illustrate that the fact that these are three independent effects there. And once you do that, you'll realize that the QC, the main heat pump effect there, is pretty amazing. It's about 23 watts per ampere, and it's quite a significant effect, and probably more than what our kind of human brains would expect. It's a bit like I use a lot of water for my experiments here, as well as the air conditioning system there. I know that the heat capacity of water is 4.2 joules per milliliter per Kelvin. I typically think that's a fairly big amount. But then if you look at the figure for just evaporating water, like changing from a liquid to a gas or gas to liquid, it's 2,250 joules per milliliter. It's like 500 times bigger than the heat capacity of water. And then things like burning wood, 1 gram of wood, 16,000 joules. Or the ultimate one, maybe a nuclear power plant where 1 gram of uranium, 80 gigajoules. They're huge amounts, and they're just a lot bigger than what our brains can work with. Now, for a Peltier, of course, is a lot smaller than the nuclear option, but at least with this, it is reversible. So not only reversible, but reversible in a very small package here. So for me, I think they are pretty fantastic items. Okay, end of all the science stuff there. I do want to do a few housekeeping things here, so I will be making videos on my air conditioning system, as well as some of the other projects like my butter cooler, my speedy beer can cooler, as well as talking about some of the interesting designs that have come up here. For example, this guy here is milled plastic that allows me to get water directly onto the surface of the ceramic of the Peltier itself, so it eliminates things like the messy thermal paste and stuff that you have to deal with. There's other designs for cell designs that I played around with. So I'm putting all of those into future videos, hopefully a lot shorter ones. For people that are interested in contacting me, just questions about Peltiers, you can either use the comments down below, or you can go onto my website, thepeltierpower.com. You'll find my email there if you want to contact me directly. And a little bit of self-promotion here. If you are working with these guys in a professional nature, and maybe you want some consulting, or maybe some bench testing, or some test equipment that I've been using for my systems here, I am available for that as well. It might help me to offset some of the thousands of dollars that I've spent playing around with Peltiers over the last few years. But anyway, for that kind of thing, just jump on the website there and find my email, and we can hook up that way. All right, that's it for this one. I hope you have enjoyed it, and I will see you next time. So see you later.